How does a vessel built for the stars, a cosmic bridge sanctioned for an unprecedented future, find itself immediately entangled in the unforgiving realities of its own home world? The Federal Aviation Administration, in greenlighting Starship, allows for up to 44 Super Heavy launches annually from LC-39A. Yet, an extraordinary demand shadows this approval: 88 annual landings. This stark imbalance, this terrestrial bottleneck, is where the journey truly begins. The implications of this math are stark. A single Mechazilla tower, an engineering marvel designed to catch a returning rocket, quickly becomes a fragile point of failure. The sheer mechanics of such an operation necessitate a second landing option, not merely for convenience, but for survival against the universe's relentless demands for redundancy. Starship's return to Earth is a brutal testament to its power. Its acoustic energy alone, 10 times louder than the Falcon 9, creates an operational pressure wave around the pad that screams for relief. This immense force alone demands additional recovery options to mitigate pad congestion and maintain any fragile rhythm of progress. The empty upper stage, a titan in its own right, weighs 5 times Falcon 9's dry mass, demanding a landing system of unimaginable resilience. Here, the engineering truly confronts the abyss. 6 massive stainless steel legs, meticulously forged from specialized 304L or 30X steel, must spread across a 15 to 18 meter footprint. These are not mere struts, they are the very sinews designed to absorb the insane landing forces generated by 3 Raptor engines, delivering a staggering 840 tons of thrust during touchdown. They must survive the fiery crucible of re-entry heat, brace against the extreme chill of cryogenic temperatures, and absorb impacts many times greater than those experienced by Falcon 9. This prevents a catastrophic tip against the moving deck of a drone ship. Their automated extension and retraction, whether hydraulic or electric, is a precise dance on the razor's edge, a critical function, demanding flawless execution in an environment that allows no margin for error. The evolution of drone ships, from experimental platforms to what must become the bedrock of a global logistics network, underscores a brutal learning curve. Equipped with 4 360-degree thrusters, they are vital for maintaining precise latitude and longitude. Yet, paradoxically, they are passive in pitch, roll, and heave, a cosmic irony. This creates a razor-thin margin for error, a required 10-degree straight-up landing against the unforgiving tilt of a 3-degree rough sea. The mass penalty for these intricate leg systems, dozens of tons, translates directly into a 10 to 20-ton reduction in vital payload capacity. This is a significant sacrifice, demanded by the unforgiving laws of physics. Weeks of transit and manual refurbishment at distant ocean landing sites further slow the pulse of progress, creating yet another constraint. Yet, these arduous steps are not without profound purpose. They offer crucial operational redundancy for invaluable human crews or high-value cargo, preserving them from destructive water splashdowns. By 2026, a fleet of at least 8 dedicated transport vessels, supporting 4 distinct landing zones, will stand ready. This isn't merely infrastructure or advanced logistics, it is Earth's crucible, actively forging a hardened global network. This network must be capable of withstanding Earth's own harsh environments, preparing humanity for the infinitely harsher, colder, and more brutal frontier beyond. What profound lessons will Earth's gravity teach us before we truly leave its embrace?